Let's learn how to draw graphs for vertical projectile motion. As of now, we know that we can describe vertical projectile motion using the position time graph, the velocity time graph, and the acceleration time graph. In grade 10, you learned about constant acceleration graphs when we were describing rectilinear motion. In this chapter, we're going to apply that knowledge when we're going to describe the vertical projectile motion. Let's look at important notes about these graphs for you to know by heart. To change any graph from taking up as positive to down as positive, or vice versa, you have to reflect it about the x-axis. Now, if you do mathematics, you know what this means. Let's say you get a graph whereby down was taken as positive and you want to make it up as positive. You just have to rotate the entire graph about the x-axis. The slopes and areas under some of these graphs will tell us about changes in other quantities. The slope or gradient of the displacement time graph represents the velocity. The slope or gradient of the velocity time graph represents the acceleration. And the slope of the acceleration time graph doesn't give us anything because it is 0. The area under the displacement time graph doesn't represent anything. The area under the velocity time graph gives us the change in displacement. The area under the acceleration time graph gives us the velocity. It is very important to choose the direction when drawing a vertical projectile motion graph, and you always have to indicate whether you took up as positive or down as positive in your answer. Please note that when drawing change in displacement time graph, you have to remember to choose a reference position. Sometimes in a question they tell you to choose the ground, for example, as the reference. But remember to indicate that because your reference position is always going to be your 0 displacement. Okay, let's look at how to draw graphs for a dropped ball. We'll take downwards as positive. But remember, if you prefer up as positive, you just have to rotate the graph about the x-axis, or in this case, about the change in t-axis. In this example, I'll choose the reference or the 0 height as the position the ball was dropped. So this means my maximum height on my graph will be at the ground position. First, let's look at what happens and then I'll explain after. Remember, you can always rewind the video to see what really happens in the animations. And you can always stop the video to see how the graphs look at a certain point. Now let's focus on the displacement time graph. The reference position is where our graph will start on the 0 displacement. Remember, the velocity of a dropped ball is 0 meters per second. So this tells us the starting point, or where change in y is 0, the slope of the graph should be 0. So if you're doing mathematics again, you know what I'm talking about. And the slope continues to increase, as we know that velocity will increase as the ball goes down. Now, if we look at the velocity time graph, you can see that the velocity starts at 0. This means that the velocity initial is 0 meters per second because the ball was dropped. The velocity continues to increase in the downwards direction because we took down as positive. It means the entire graph of the velocity time graph should be above the t-axis. Our final velocity when the ball hits the ground will be represented as Vf, and it's a bigger value because the velocity increases from 0 when we drop it until a maximum value when it hits the ground. An acceleration time graph will be 9.8 meters per second for the entire motion of the ball. Because we took downwards as positive, acceleration is going down and it has a constant value, so we have a straight line for any time. Let's look at the motion of the ball again and the graphs when they are drawn in real time. The position time graph is a parabolic graph with the gradient representing the instantaneous velocity at any time interval. The velocity time graph is a straight line with the gradient representing the acceleration of 9.8 meters per second squared. The acceleration time graph is a straight line with zero gradient. Let's look at a case whereby a ball is thrown downwards. For this example again, we'll take downwards as positive and I'll choose my reference position as the position where the ball was dropped. Let's take a look at how the graphs will look like in real time. So you can clearly see that the motion of the ball is quicker because the ball was thrown at a certain velocity. Let's take a look at the position time graph. Remember that the gradient of the position time graph represents the velocity, and if you check the gradient on the point where the change in y is 0, you can clearly see that the gradient is not 0. It is some value. This means there was initial velocity given to the ball. You can clearly see the difference between this change in y-t graph and the previous one. Let's move over to the velocity time graph. You can clearly see that there is an initial velocity that we marked vi. As we chose down as positive, this velocity will be positive because it is thrown downwards, and the velocity continues to increase until the velocity whereby the ball hits the ground, which we denoted vf, which is also in the downwards direction. We get a straight line graph of gradient 9.8 meters per second squared. If we look at the acceleration time graph, we can clearly see that the acceleration is still 9.8 meters per second squared. We see it is a positive value because we chose downwards as positive, and acceleration is always going downwards. Let's look at a case where a ball is thrown up and returns to the same position. For this example, we'll change and take upwards as positive. I'll choose the reference as the ground for this example. Let's look at how the graphs are drawn in real time. For the displacement time graph, remember we chose upwards as positive and our ball never goes below the reference, so our graph will always be above the change in t-axis. And for this case, just remember that when upwards is chosen as positive, the graph will reflect exactly the motion of the projectile. So in this case, the ball is going up to a maximum height and then dropping down below to the reference position. So that is how our change in y-t graph is going to look like. For the velocity time graph, remember when we throw a ball upwards, we give it initial velocity and we chose upwards as positive. So our initial velocity should be a positive number. As we can see, when time is 0, vi is positive. Now when something is thrown up, it continues to lose velocity until it gets to a highest point where its velocity is exactly 0 meters per second. This is why we see our graph going from initial velocity of a positive value, decreasing all the way to 0 at its maximum height. Now from the maximum height, the ball will continue to drop until it reaches the ground again. So we see the velocity starts to increase in the downwards direction until we reach a final velocity, which we denoted vf, which is going down, and we chose up as positive, so we expect that value to be negative. Another important thing that we know is that vi is equal to vf in magnitude, because when a ball is thrown and it returns to the same position, the velocity at that position will be the same. Now, if we look at the acceleration time graph, we chose up as positive, so our value for acceleration is negative 9.8 meters per second because acceleration is always going downwards, and we see it's a straight line of value negative 9.8 for any time. Now let's look at a ball that is dropped and it bounces. We will mark interesting points A, B, C, and D on our graph and on the motion of the ball. In this example, we'll take upwards as positive. We'll choose the reference position as the bounce position or position B. Let's look at the graphs represented in real time. Let's go through the motion of the ball. So the ball was dropped at point A. So this means the initial velocity there is 0 meters per second. The ball will bounce at position B and go to another highest point at position C and continue to drop until position D, which is below the reference position. If we look at the position time graph, we can see that the bounce position or position B is on 0 meters. The ball will drop until it bounces at B, goes to a high point at position C, continues to drop beyond the reference position and goes all the way to position D. Remember, if we take upwards as positive, the displacement or the position time graph is exactly the motion of the ball. So you just copy that and paste on the graph. For the velocity time graph, we can see that the first velocity at time 0 is at position A, whereby the velocity is 0 meters per second due to the fact that the ball was dropped. The velocity starts increasing in the downwards position, but remember we chose up as positive, so we expect that phase of the graph to be below the change in t-axis. The velocity will continue to increase in the downwards direction before it bounces on position B, which will denote the velocity as VB down. There is a slight discontinuation due to the fact that when a ball is bouncing on a surface, it is going to spend a split second in contact with that surface, whereby the change in displacement for that time is 0 and the change in velocity for that time is also 0. That is why we see a discontinuation at position B. Now, at the instant when the ball bounces off the surface, it is going to leave at a certain velocity, which will denote as VB up, because the ball is still at the same B position. Remember, we took upwards as positive, so VB up will be a positive number. The ball continues to move upwards while decreasing speed, going towards the maximum height, whereby the speed or the velocity at the maximum height will be 0 meters per second. This is at point C, after which the ball will start to increase in velocity in the downwards direction until it reaches point D, and will denote the velocity at point D as Vd on our velocity time graph. Now let's jump over to the acceleration time graph. From position A to position B, acceleration is negative 9.8 meters per second squared. But something interesting is happening in position B, as we've seen with the other two graphs. In this case, during the instance when the ball is in contact with the wooden block, it experiences a force pushing it upwards, which is going to result in an upward net force, making acceleration go in the upward direction. But as soon as the ball leaves the block, acceleration resets to negative 9.8, then the acceleration continues to be negative 9.8 until position D. And guys, we'll do more examples and more questions in the future, but these are all cases or all examples that you need to know. Now I'll play the animations again for you guys to visualize. Here is the dropped ball example again. Here is a downwards thrown ball example again. Here is a ball that is thrown up and returns example again. Here is a bouncing ball example again. Okay guys, please like the video and comment, also subscribe so that you can see future videos. Thank you guys for watching. Cheers.